Okay, so these three objectives are what we're going to do today, and then that one's the one we'll do tomorrow. All right? Joe, you want to borrow a pretty color? Okay. All right, so vocab. Okay, a function is one-to-one if any two different elements or inputs in the domain correspond to only one element in the range. So basically what it's saying is that if I have for my function an x1 and an x2, then my y values, or f of x1, cannot be the same as my y value for x2. Okey-dokey. All right, so horizontal line test. It determines if your function's one-to-one. And if you're doing horizontal, then you're taking your pencil this way instead of vertical. All right, and if it intersects the graph at most one point, then the function's one-to-one. Okay, so let's say I have a graph that looks like this. Okay, and I do a horizontal line test here. I have two intersection points. So it's not one-to-one. Okay? However, if I have a graph that looks maybe like this, and I do a horizontal line test anywhere, and we have one intersection point, so it is one-to-one. Are we good? Ready? Okay. Who remembers what an inverse is? We found an inverse when we were doing our identities in the matrices, right? What was the symbol for an inverse in our matrices? Yeah, the -1. So like for our matrices, our matrix A, the inverse, we showed it as the -1, right? Okay, so what does an inverse actually mean? Kind of yes. It kind of yes is the opposite. But basically, what it says is that for each x in the domain of f has exactly one y in the range of f. Okay? So for the inverse, the correspondence says that from the range of f back to the domain is called the inverse function. basically what that's saying is that if we have the function of x and it has an xy, then the inverse of x is going to be yx. So, well, yeah, it's opposite, I guess, I don't know, it kind of describes that, but basically you just flip your domain and range. Okay, so it is kind of the opposite. Does that make sense? I don't know, opposite to me kind of has to go with the symbol, but it's like the flip of the ordered pairs. Okay, so to find the inverse of it, the easiest way actually is to do your domain and range, because that's your x and y, right? So in order to find, we'll call this one's the f of x is this set of ordered pairs. Okay? So my inverse, I literally am just going to flip my ordered pairs. So, yeah, that's the negative one showing the inverse. So I literally just flip my ordered pairs. So the inverse of 0, 12 is going to be 12, 0. The inverse of 1, 11 is going to be 11, 1. The inverse of 2, negative 6 is going to be negative 6, 2. The inverse of 3, 5 is going to be 5, 3. And then 4, 13 will be 13, 4. Okay. So if I find the domain for the f of x, it's going to be 0, 1, 2, 3, and 4. And my range is going to be 12, 11, negative 6, 5, and 13.
So it's the domain of the original.
That's the domain of the original. So if I want to find the domain of my inverse, all I'm going to do is look at my range and say, hey, it's going to be 12, 11, negative 6, 5, and 13, which then gives me the range of 0, 1, 2, 3, and 4. Does that make sense, Alex? Good? All right, let's look at the graph. That's if you just have the like ordered pairs. Let's look at the graph. Okay, we got a 1-to-1 function there. And if I want to graph my inverse, okay, because it's 1-to-1, I'm going to flip-flop my ordered pairs, which, if you go back in your memory banks to geometry, remember geometry? Okay. It makes it symmetric about the line y equals x. So here's my y equals x kind of thing. Okay. Now, if you remember from geometry that the distance is from your line of reflection, that means that this point right there is going to stay right on the line of reflection. So it's going to be exactly the same. Okay. If you don't remember all the stuff about geometry and the distance from the line of reflection, you can just look at your ordered pair. So my f of x is 2, 5, negative 4, 1, 1, 2, and negative 5, negative 5. Okay. So my inverse, I'm going to flip-flop my ordered pairs. So I have over 5 and up 2. And then I'm going to have 1, -4. So over 1. Oh, I'm sorry. Yeah, no, that's right. 4. And then I'm going to have 2, 1. And like I said, since this is on the actual line of reflection, even if I flip-flop it, it still stays the same. And then when I connect my points, helps if I graphed it right. Where's my 5? Got that graphed on the line. Make sense? All right, so yeah. Okay. All right, so how do you do it when you have just an equation? You don't have the graph on there, it's just the equation. So let's graph the first one. Let's graph the equation. So what kind of function is that? It's slope-intercept, so it's linear. How do we graph a slope-intercept linear equation? Start at 3, and then we're going to go up 2, 3, 4, and over 1. And I'm going to also go down 2, 3, 4, and over -1. Okay. And go 1, 2, 3, 4, and over -1. So I have 4 points. Okay, so now I can graph my inverse. So if the first point I have 1, 7, my second point I have 0, 3, my third point I have -1, -1, and my fourth point, I have -2, -5. Okay, let's draw our line of reflection. So that starts at the origin, right? And it's a slope of 1. So there's my line of reflection. Yeah, and if you remember a line of reflection is where you're going to have, if you actually took the paper and folded it in half because it's symmetrical, that means that this part's going to be over here, this part's going to be over there, because it's like your mirror, it flips kind of thing. But it's sometimes easier if you have your points, just flip your points. So 1, 7 is going to become 7, 1. So if I go over to 7 and up 1, that gives me the same distance to my line of reflection on the other side. 0, 3 is going to become 3, 0. which again, I got the same distance to my line of reflection. -1, -1 stays the same because it's on the line of reflection. And then -5, -2. And so now it looks like the symmetrical reflection. Good. Okay, so what's my domain of my original function? All reals, absolutely. And what's my range of my original going to be then? All reals as well. So my inverse domain and range is going to be all reals as well. Okay, good. All right. Let's do one more. What's x cubed look like? What kind of graph is that? Nope, it's not parabola. That's a quadratic. That's the it's the little squiggly line. All right. So if you don't remember how that looked, what's another way to go about graphing it? Besides your calculator. Pick some easy points. So if this is my f of x, let's say -1. That's an easy enough point. -1 cubed is going to be -1. -1 plus 1 gives me 0. Right? 0 gives me a y value of 1. Everybody with me? 1's going to give me a value of 2. And 2, because it's asking for 4 key points, gives me 9. So now I can graph it over 1 up 2, over 2 up 9. And I go, oh yeah, I remember. It looks like that. And that's what I mean by my roar. It just kind of goes up the line. Okay, my line of reflection is still going to be my y equals x. So again, I can look at it. This point's going to probably be somewhere over in here. This point's going to be somewhere over in here. These are going to be somewhere over in there. But if we just make another table, because I'm going to flip-flop my points around. So I have 0, -1. 1, 0, 2, 1, and 9, 2. Good? So, over 0, down 1, over 1, 0. Oops, let's do it in another color. Over 2, up 1. Over 9 up 2. I think I'm going to do like a -3 just to see. Let's see, that'd be 27. you're right, -26, so it's gonna be way down here. So, -26, -3 is gonna be here. That gives me an idea. Not as good at drawing my curve lines. Sideways. Good?